So today we're going to be talking about capacitors. Now this is a topic that we felt gave us a bit of trouble on the AP exam because a lot of the stuff you need to understand with capacitors is conceptual, and many people don't have real world experience with capacitors and don't fully understand what they do and how they behave under certain conditions. So we came up with an analogy to try and change that. So here we have a water bucket, and it's completely closed, so the water can't go anywhere. The water is not going to leave. In this analogy, the amount of water represents the amount of total charge in the capacitor. The height of the water represents the voltage of the capacitor. And the cross-sectional area of the water represents the capacitance of the capacitor. So what happens when we half the distance between two parallel plates in the capacitor? Well, the total amount of water in the capacitor, or in the bucket, doesn't change. However, the voltage of the capacitor does change, because as we push the top and bottom together, the height changes and the cross-sectional area gets bigger. So the voltage goes down, and so if we compress this to a height of 1/2 the original height, the voltage will drop by a factor of 2, and the capacitance will go up by a factor of 2. So this is a good way to conceptualize what happens to a capacitor when you change a certain factor, because as we can see here, it's actually quite simple to think about what would happen. But if you're thinking only about what would happen in a circuit where you don't really have as much experience and it's harder for you to imagine in your head, it might actually be quite hard to determine what's going to happen. Now we're going to be discussing, using our analogy, what happens when the amount of charge on a capacitor is doubled. So in this case, since water represents the total amount of charge, the question is really, what happens if we double the amount of water that's in here? So basically, when we're doing this, we aren't really changing any physical properties of the water bucket. We're just adding more water, and so for that reason, you can kind of imagine that the capacitance of the capacitor doesn't change, and that would be true. So in this sort of analogy here, if we double the amount of water in it, the water will just fill up more of the bucket, so the water will be filled higher in the bucket. However, the actual surface, or the cross-sectional area of the bucket, will not change, meaning that our capacitance will still be the same. And as we discussed earlier, we have 2Q as the amount of water or charge on the capacitor, and we can also see that the voltage, which we've discussed as the height of the water, will be 2 times the original voltage. Here we have a sample problem involving capacitors, and basically our question is, what happens to the circuit after it's been sitting for a long time, after the capacitor and the resistor have been hooked up to the battery for a long time? So we can use our water bucket analogy in order to conceptualize this. So we know, due to Kirchhoff's loop rule, that the maximum voltage that the capacitor can have is going to be the same as the EMF of the battery, because the voltage differences have to sum to 0 in a circuit. So we can label this. Now we can also think of the wire in the circuit as carrying charge or water into the capacitor or bucket. So we can think of that as a hose. And basically the hose is filling up the capacitor. Now, once the capacitor gets completely filled to the level where its height or voltage is the same as the voltage of the battery, then it stops because the circuit is now completely in equilibrium and everything just halts. But if we think about the circuit during the time from the beginning to the end, we can see that the water level is going to rise as the current moves through the circuit and just fills up the bucket and the capacitor, and it just keeps charging the capacitor over time. So the capacitor gets fully charged. Now that we know what happens to a capacitor over a long period of time, we can write an equation for the voltage across the capacitor, and we can find that at any time from t equals 0 to t equals infinity. So let's write this function. We're going to call this function v sub c of t. And we know that when t goes to infinity, v sub c of t is going to be equal to the EMF of the battery. So we know that this equation can be modeled by multiplying the EMF times a certain function. Also, as you guys have learned from class by now, the function has to include e to the negative t over tau. And this goes to 0 as t goes to infinity. So the way we model this, since we know it's going to EMF, and we know that at t equals infinity, EMF has to be multiplied by 1. We know that EMF has to be multiplied by 1 minus e to the negative t over tau, where tau is our time constant, which is equal to r times c. This is actually quite easy to figure out. Once we figured out what was going to happen to the circuit over a long period of time, we know what this value, this constant value, is going to be, and then we can model our equation, our function after that, as we know that as t goes to infinity, this function has to go to EMF.
We're going to explain inductors, which are a pretty complicated idea because they involve differential equations, flux, inductance, and a lot of other really big words. So I'm going to try to explain this very simply. So for a resistor, a given resistor will have a voltage proportional to the change in charge that goes through it. So we define its resistance as the voltage for the current, which is the same as dq dt, change in charge. For an inductor, it's a very similar story. Its voltage is going to be proportional to the change in current over the change in time instead of charge. So we define its inductance to be the voltage over the derivative of current with respect to time, which is very similar to a resistor. We wrote it before as voltage for a change in current, but people will write that in terms of EMF, which is the same as voltage, and then they'll use Faraday's law to write EMF as d phi dt. But even though you'll see inductance defined this way, it's really the same as V over the derivative of current. And there are two equations basically only that you'll need to know for inductance. So the first equation is going to just be the definition of how you calculate inductance for an inductor. And that's what we talk about here and here. The second equation is for the potential energy of an inductor. And it's just equal to 1/2 Li squared. And this is very similar to a capacitor, which has a potential energy of 1/2 CV squared. And you don't really need to understand this conceptually.